Good afternoon. Hello.
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 Welcome to the webinar. So ThinLinc HPC community and Cendio welcome you. And today the topic we are going to discuss is Interactive HPC at LUNARC, presented by Anders and Jonas. So thanks all of you for attending. A brief introduction, why we are here today, how everything started. So in February this year, some academics joined efforts and submitted a BOF proposal to ISC 2020. The idea was to discuss interactive supercomputers. And as all of us know, the plans for ISC changed, but the interest in discussing the topic remained. So as a consequence, these webinars are now happening. And we wanna express our gratitude for all of them that helped this, made this happen. So now today is the third webinar. The first one was with Bernd Lindemann from the Technical University of Denmark, and the second one in June with Robert Henschel from Indiana. So now the third, we have confirmations of representatives from industry, academia, and governmental organizations from different countries. So thanks all of you for coming. Here, there is a brief abstract of the presentation today. It was shared with all of you. I hope you had access to it. So, Interactive HPC at LUNARC. So, who are Anders and Jonas? So, Anders Follin is Deputy and Technical Director at LUNARC, and Jonas Lindemann is Director at LUNARC at Lund University here in Sweden. So I think they will detail more about their biography during the presentation.
Yes.
Some instructions. It's a long slide here. We estimate a total time of 60 minutes, being more or less 30 minutes for the presentation and demo. So today we have a demo. And 30 minutes for the discussion. Of course, if you want to continue the discussions after 60 minutes, you are welcome to stay. The session is recorded. However, the recording will only be publicly shared once Cendio has the express permission from everyone that has been active in the session. During the presentation, we invite the audience to turn off the microphone, aiming to reduce noise pollution. And also remember to take notes and save your questions for the discussion part. During the discussion, your active participation is welcome, and of course it enriches this part. You may contribute directly to the discussion if possible, or write down in the chat. Please remember to turn on your microphone when asking questions and introduce yourself briefly. Long presentation till now. I think it's time to transfer the screen to Jonas and Anders. Are you there?
Yes.
Yes.
So welcome.
Thank you very much.
John.
So I will send it to Megan. Can you see our screen now?
I see your screen.
Yeah.
That's a good start.
Yeah.
So I will start here. So this is a talk called Interactive HPC at LUNARC. And the subtitle is Providing a User-Friendly and Scalable Desktop Environment for HPC and Visualization. So that's the main what we're going to talk about. So who are we? So my name is Jonas Lindemann. I'm director of LUNARC. I have originally a background in structural mechanics and did my PhD a couple of years ago, but has since transitioned to working on with the high performance computing at Lund University. I have also teaching a lot, basically Python, C++, and Fortran. I'm also the developer behind a tool that we're going to show you later called GFX Launcher, and also some other tools that we have developed. So, Anders.
So, hi everyone, my name is Anders Follin. I'm the, as John said, the Deputy Director and Tech CTO of LUNARC. Before I joined LUNARC in 2010, I was with Silicon Graphics, or SGI, for 15 years doing graphics in EMEA, ranging from everything from oil and gas to manufacturing industries and defense and simulators and such. And the last few years, we spent a lot of effort into doing those early days remote visualization technology for our product. So I brought some of those ideas into LUNARC when I started in 2010. Okay.
So a little bit about LUNARC. So we are a supercomputer center located at Lund University. We are a member of the SNCC National Infrastructure for Computing as well. We originally founded by researchers for researchers. We don't come from the IT departments. We were a center kind of founded by a need for researchers to do large-scale computing. So we provide high-performance computing, storage, and visualization resources. We also have a lot of experts working at LUNARC, providing specialized knowledge for parallel programming, Python programming, scripting, and so on. We also do a lot of implementation projects with our research communities at Lund University. A lot of training, which is very valuable, very important for engaging with the users and getting them to use our machines. And we support Swedish research on all levels. We also provide special HPC resources for handling sensitive data as well. Yep.
Okay. So I talk a bit about LUNARC and what we're doing in the remote viz area, and give an introduction to the technologies that we have and provide. So our remote viz journey started back in 2010, as I briefly said before, and we envisioned that there was an increased need for a better way, a more user-friendly way to access HPC systems. And the two of us, me and Jonas, we had many years in both architecting, development, also implementing graphic solutions, and also to a certain extent remote visualization environments, both in academia and industrial environments. And there's a lot of reasons to this, but to pin down to the major reasons, I would say that all the classic things apply here. So remote hardware accelerated viz is important because you can keep the large data sets in the data center and don't stress network bandwidth and shorten lead times because you don't need to copy things across. And since computational engineers, and by the way, I'm also a structural engineer from the beginning, you always would like to have high precision, meaning the larger data sets ending up in the larger output data for post-processing. So meaning that you stress the bandwidth even more if you wanted to copy the data set to your local workstation, and you probably need to partition it into small chunks and visualize each chunk separately. And it's easier to secure the management of sensitive data as well if you keep everything in one place and you avoid redundant copies. License consolidation is another reason why it's good, because you can have floating licenses and share licenses among more users. And there's more reasons why we all know this is very beneficial. The second reason is that HPC has always been very, well, not secret, but very for specific users, and then very delicate reasons for using it. And we would like to broaden the usage by giving users access to graphical user interfaces to the HPC backend. And we have, can we remove this because I can't see? Okay, thanks. So we have built, we're using both the built-in desktop standard applications, of course, file managers and etc., as well as some custom developed tools, the module browsers, specific storage explorers, and other things to give the users a graphic view of the system. And last but not least is the disconnect reconnect feature that actually in itself is actually a massive improvement in usability, because you can disconnect, go and get home, and you can reconnect to a desktop that's actively running. So that in itself has been a very important feature for our users. In the beginning, we did evaluation and some proof of concept for some different solutions in the early years, 2010-ish. We had a setup with PCoIP protocol from Teradici. Was very well functioning, high performance, but it had a need for both a host adapter and hardware thin client on the user side. And based on our usage scenarios and how our users are working, it was not an ideal solution. We also did some tests with the new machine NX that uses compressed X, and of course open source VNC that ThinLinc to a certain extent is based on. But we ended up with Cendio, and there's many good things with ThinLinc, and two of the good things is that it's a supported solution for what we say our 2D pixel transport. And then we have built our own custom backend, so it's good to have a supported solution with very good support for our pixel needs. And it also supports out of the box, or has out of the box support for our flavor two-factor authentication that comes from a Swedish company called Phoenix ID. So the current state of the desktop, we will drill into this during the presentation, is that we have a remote desktop solution, RV solution based on ThinLinc that's been in production since 2013. It's accessible from all client platforms, Mac, Windows, Linux, and iOS using HTML5. We have a custom architected scalable backend providing both 2D and 3D applications with hardware graphics acceleration. And we have a recently developed on-demand system or service for requesting dedicated nodes for graphic use by our queuing system, which is Slurm. We use the same for the standard cluster for compute. And we can provide accelerated graphics with, I would say, any OS, all assembled into the 2D ThinLinc XVNC desktop. And we have a huge amount of software, and it's installed upon user request, and it's constantly increasing. And we have actually a very large user base. So I'll give you a very quick overview of the LUNARC architecture of the data center. Of course, as we can see, we have more than 1, 2, 3, 4, 5, 6, 7, 8 boxes, but I omitted everything that is not in this context. So as I said before, we have Phoenix ID two-factor authentication. We're using two different catalog services. We used to use OpenLDAP, but moved into Red Hat IDM, Identity Management System, some years back in time. And in addition to that, we have AD for the Windows side of things. On the left-hand side of the slide, you see the Aurora Compute Cluster. We have Elvis, that is a bare metal on-demand graphic cluster with 24 graphic nodes with up to 8 GPUs per node. On the right-hand side, we have the 2D desktop agent, that is the ThinLinc agents. We have some shared graphics application servers, and we have a hypervisor-based on-demand graphics cluster. And in the center, we have the storage. We have 4 petabyte IBM Spectrum scale GPFS file system, and I won't say too many, but still direct attached NFS storage pools for miscellaneous storage. It's a Phoenix ID that gave us the higher security. So for all connections, both SSH terminal-based and also all desktop-based connections, we use second factor. We used to use SMS, but now we're using Phoenix ID's Pocket Pass OTP. So So it's a token that is generated on the smartphone. The spectrum scale connects using InfiniBand and using native GPFS client for all Linux-based systems. And the Windows systems use SMB2 and Ethernet, either 1040 or 100 gigabit. We have NFS also using Ethernet for NFS clients, for those clients that don't use the native GPFS clients, and for other purposes, other kind of servers. From a catalog point of view, IDM is used, of course, for Linux, and we're using CentOS as our main flavor. Microsoft 80 is used for Windows boxes. And to manage two different catalog systems, we ended up in this configuration that also is a high-level sketch. IDM is our main catalog service, so all users are first populated in IDM. And we had an automatic process that populates the Microsoft 80 using the same UID GID and the first factor, the password, that populates the Microsoft 80. The 80 is joined to, oh, sorry, the data is served from the parallel file system, the GPFS file system, and we have a protocol server attached. The protocol server talks natively with the GPFS to the spectrum scale file system, and we have one SMB server and one NFS server running on the same box. And the SMB server is joined to the 80 domain. This solution manages to serve Windows boxes with the data using the SMB2 protocol, and the cluster side of things uses GPFS, the Linux side of things, and also NFS for some other not that performing Linux clients. Okay. So the net result of all this is that we can provide a desktop where the 2D desktop is ThinLink's excellent desktop, and we ingest accelerated pixels from various sources and assemble them into one canvas, rendering canvas that is brought to the users by Cendio, ThinLink. And all these different app windows, independent on which OS they run on, have access to the central storage file, the central file system using GPFS, or spectrum scale that it's called these days. So one good thing here is that if a user, for instance, runs a parallel computation of whatever, could be CFD computation, he or she can access the data, as the data is stored on the central file system, then he or she can start a Windows-based post-processing app and access the same data. So go back and forth between different doses. So the evolution of what we've done here in our VIS. Well, this is not VIS, it's a terminal session, but this is actually the extreme classic SSH. And this is completely obvious for everyone, but you connect to the front end using SSH, and we're using the two-factor authentication to achieve a high level of security. The next level in this on this journey is to use ThinLink's sort of standard desktop, which is very well performing, of course. Not of course, but it is actually very well performing. And it's the same authentication process where the user authenticates using two-factor. And we have a couple of desktop agents that uses Cendio's load balancer mechanism to put users on the least loaded agent node. And that it delivers to the desktop to the end user. This is also very well known for all ThinLink users. The next step involves some custom development made by LUNARC. What do you mean, Jonas? And it's the accelerated 3D desktop. It uses the standard 2D desktop and introduces a concept that we call graphics application servers. So in this screenshot, what we see here is that we have the background is, of course, the XVNC server by ThinLink, and the ParaView window with the colorful image is rendered on a separate system. a graphic server, in this case GTX 0, and the pixels are injected and assembled into the desktop. So it works like this. We have the same authentication and the same agent setup. And when a user starts a specific app, that specific app is running on a dedicated application server, and the selection of server is depending on the application launch. So for instance, if an application has high demand for RAM or fast CPU cores or specific accelerator cards, an application server is chosen that has those features for the specific app. And as said before, the output with the accelerated pixels are assembled into the 2D desktop and sent through to the user. So how does this work? Well, on the left-hand side is something that won't work. First of all, we can't have workstation cards in the server, in the data center, because we have no it's server class, data center class servers. So we need something else, and we couldn't either pull some sort of DVI extension cable through the campus. That would look really weird. So we're doing something else, and typically we have V100 and P100 cards, server cards from NVIDIA that are passively cooled by fans inside the server. And I assume this is also well known to everyone, but we use VirtualGL for doing the rendering. So normally when you do 3D graphics on a workstation with OpenGL, the OpenGL lib talks to the X server and the graphics card, and it renders locally to the local X server, and the X server can also be distributed across the network, and that X server is on the client side. Then you send OpenGL commands through the network to the X server. But this image shows a local setup. What's happening in VirtualGL is that the OpenGL inserts interpretation label that snoops listens to the OpenGL stream and replaces certain calls in the stream. And instead of sending it to the X server across the network, it sends it to the X server that renders locally into P buffer, a pixel buffer. And the pixel buffer is transferred across the network to the X server. That in this case is XVNC by Cendio. This is true only for Linux applications. This won't work on the server side for other OSs. Okay. So the server client model is like this. We use this server client model to execute applications and establish the pixel transport with a VGL transport from the app servers to the 2D desktop agent nodes. And the accelerated pixels are then assembled into the 2D space on the agent nodes. The client scripts are launched from the custom-made applications menu in the ThinLinc desktop. And the client script establishes this VGL transport pixel transfer from the application server and also executes a server script. And the server script executes the actual application wrapped by VGL run. And we have different app servers depending on the needs, and we have a load balance setup where we have multiple servers to divide users on more than one bare metal server. It's still, however, static, and resources are shared. So if more than one user running a specific application, they are sharing the same hardware, which introduces competing. Very solid actually, and it's well performing since the start 2013. Last year we decided to do something slightly different. So we looked at how we're doing things on the compute side of LUNARC in Aurora, the compute cluster. And we decided to do transition to scheduled resource management also for graphics. So this allowed We can schedule on-demand graphic resources. We can have selectable wall time and selectable feature sets of the resources that we are able to schedule through Slurm. Another cool thing is that when we schedule a resource, the user owns the resource for the wall time period of time. So it's not a shared resource, meaning that you can do whatever you want, well, almost whatever you want with the server, and when the wall time is up, the system is reset for the next user. It's very flexible and also enables secure visualization of sensitive data because you own the system, or we can do special take care of the system of it's used by the first user to make it prepared for the second user. And as I said, we're using Slurm. So this is how it looks like. The first generation of the on-demand desktop. So now we're running a volumetric rendering application. It's VolView. And to the left of this image, you see the on-demand GUI, where it's possible to choose different feature sets and set the wall time. And there's a progress bars. In this case, the user have used 23% of the wall time. This is how it works. It's the same authentication, same desktop agent setup, and we introduce Elvis, our 24-node bare metal graphics cluster, where the user starts an application through Slurm, and Slurm allocates a suitable node that is free on Elvis, and Elvis output is rendered using VertiGL into the 2D rendering canvas that is sent through the user using ThinLinc HPC. This is just a close-up of the previous slide. And to the left, you can see the GUI slightly zoomed in, where we can choose different GPU configurations. And as you might see, it's quite an old cluster. This specific cluster is from, I think, 2012, and it has K20 GPUs and some different memories, specific nodes, memory specification of the nodes. Okay. And then the last incarnation of the on-demand desktop introduces, in addition to bare metal servers, we can now run virtual machines or hypervisors, which open up possibilities to run other OSs that doesn't cope with VertiGL, such as Windows. So in this image, to the left is your pair view running on one of the application servers, the bare metal servers. The background is, of course, a good old ThinLinc running on the agent node. And the top window is Windows 10 running Imaris. It's a bioimaging application for microscopy. Both apps are running, are using accelerated graphics and ingested into the 2D desktop. Now we're running Windows, but of course we can run any OS in the hypervisor. So how does this work? Well, it's the same, once again, authentication and desktop agent setup, but in this scenario, the launcher, the GPX launcher that Jonas will describe later, has acquired a virtual node running on the hypervisor. And we can mix experimental nodes, the yellow ones, with hypervisor nodes, the purple ones. And it ends up like it is on the right-hand side with the VM-based application or OS running application together with the bare metal system running, in this case, ParaView. The hypervisor node architecture, we're using SenServer or Citrix hypervisor. And the hypervisor config is like this. We have hypervisor with dual NVIDIA V100 GPUs. We can choose either to do a pass-through of the graphics to one VM. Here, I passed it through to Windows 10 VM. And or we can slice the GPU in virtual GPUs, vGPUs, with different frame buffer configs, and serve either Windows 10, CentOS, or Ubuntu. And depending on the OS, we have different protocols. We have VDL transport for Linux, and we have RDP for Windows. And disregarding what kind of protocol used, they are assembled into the desktop. That's how we can have one solid environment where we can run different OSs with different applications, all accessing the central storage. Okay, now it's Jonas.
Okay, thank you. I'll continue to kind of go through the architecture of the latest incarnation of the desktop on demand. So what it is boils down to, it's a graphical client for launching user resource selection and monitoring of the launched application. And all our interactive applications are launched through Slurm. So Slurm is the kind of key here in control of this. And you can launch interactive graphic applications, so normal X applications running on a node. And you can also launch, of course, interactive graphic with hardware acceleration. So it supports the VGL Connect and VGL Run features of virtual GL. You can also run web-based tools like notebooks and labs with automatic connection and the start of a browser on the desktop. So you start a notebook on the node, and then you connect with the browser to this node. That is handled automatically through this tool as well. And the newest feature is that it also enables the starting of virtual machines through Slurm. So we can start Windows-based instances using the same tool that we launch Linux applications. So let's see, the graphics, the application is called GFX Launcher. It basically is a command line tool that presents the user with a user interface for selecting wall time, selecting features. It automatically selects a project based on which grant file you're part of on the system. And there are some controls here for starting, closing, stopping, and some other things here. And there was also, and below there is a usage bar so that the user can see how much of its wall time has been used when the application has been started. And there's this is the user feature selection box where you can translate the Slurm configuration for the nodes into easy to understand for the user text for the resource selection. There's also a detailed resource specification here if you want some other more detailed resource usage. You can specify that as well. So what this does here, so for graphic applications, you have you define a launch script where you specify a lot of options for different attributes you want your applications to run, and then you also specify a run script that actually runs the application on the node. And the launcher submits a placeholder job to the Slurm queue and monitors when it starts running on the node. And when the job is running, it connects using VGL Connect or SSH to the node and starts the application. It can also handle non-interactive applications that are running as web services on the node as well. So for example, the Jupyter Notebook is a typical example of this. So what it does then, it submits a Jupyter Notebook to the queue, and it waits for that notebook to start up. It monitors the output and sees, okay, now it started and there is a URL. And then it connects and starts a browser on the desktop and displays the notebook. We will demonstrate this in the demos as well. So, and the latest launch method is to start virtual machines. So in this case here, you have a launch script. It submits a placeholder to a special node that we have configured for launching. So there is one node connected to every hypervisor node. And this node has special Slurm scripts for starting virtual machines. So when the job arrives, the product scripts looks at the configuration, starts up a virtual machine, writes a information file to the user's home directory for the started virtual machine. And when the virtual machine has started, it connects to this machine using remote desktop connection, so the RDP protocol. And when the wall time is over, the epilogue script shuts the virtual machine down in a controlled way, so to speak. This is how it looks. We will show that in the demo as well. So here you see the launch window and the remote desktop connection to the virtual machine. So what we do here to kind of keep track of resources is that for every hypervisor node, which can contain many different sizes of virtual machines we have set up, we create the corresponding GRESS resource in Slurm, so that you never, when all the virtual machine have been allocated, you can't submit any more jobs to that node. So that Slurm keeps track of the resources automatically for us. There's also another tool that we have developed that is part of the same tool here. There is a command line script that can generate menus and client scripts automatically from the created run scripts. So by placing special meta tags in the run scripts, menus can be generated automatically. So in this case here on the left, we have a run script that contains the LDT tags, and those are used to actually create a menu structure. So it will place this, create a menu item in post-processing subcategory, and then the paraview will be the item that will be in the menu to launch it. And that launcher will have this script added here, the graphic launch command line tool script added to the menu item. And you can also have some other, you can specify partitions and what kind of jobs as well in these meta tags. So we work together with archaeology department here, which are extensive users of the interactive desktop, especially they're using photo reconstruction. So I will just give you a short answer how this technology can be used, especially with new user groups that has not classically been using HPC resources. So the archaeology in Lund have been an early adapter of 3D photogrammetry and 3D reconstruction. In the beginning, everything was done on laptops and workstation at the department. But the problem is that the drones and the cameras on these drones were producing larger and larger images. And also it creates a large data set of images that needs to be correlated to create the 3D models. And basically, at some point, they couldn't buy any larger workstations. So they asked us to kind of see if we can help them to provide this feature on our machines. So just an overview of what they are doing. So this is a field trip we did. So this is you fly the drone over an area and take a lot of photographs. So for example, you put an area, this is what you want to scan, and then perhaps there are some historical findings here, but you can't see them, you want to search for clues. So you put the pattern here for the drone to fly, and the drone flies, takes a lot of photographs to cover the entire area. And then you put these photographs together and enter them into a program. So this is a ruin of an old church here in Sweden. And they have scanned this both with drones, but also with normal cameras. And then you end up with something like this here. You see all the blue rectangles here are actual photographs taken of this church. And then the program correlates this and creates a point cloud from these images. And this is a very, depending on how large photos you have and how many photos you have, this is a really time-consuming process that can take days to complete. This is the end result here. You get the 3D model, which we'll also show you later on in the demo. And this is the equipment they're using. So this is a DJI drone, commercial drone. And then they fly this and take photographs. And they actually upload the images to the LUNARC machines to do a preview and see if they have complete coverage. So the workflow is like this. They have the drone. They take out the SD card from the drone, upload it to their laptop, and they upload the photographs to the LUNARC resources using WinSCP. And then they use the desktop here to actually do a preview of the final calculation to make sure that they have everything covered. So it can be a lot of images. So for example, 1,000 image, 9 gigabytes, and now they are doing even larger images. So we are approaching, it's very hard to do this in a reasonable amount of time. So processing of this can take up to 7 days if you have a laptop. So if you're out in the field, you would like to be able to do a quicker sort of analysis and see that you have everything covered. So, and that they can do now by accessing the LUNARC resources. So now they can do, using the on-demand desktop, they can do a very, just take minutes for a coverage, and they can actually do the complete model in 4 hours before they are leaving the site. Yes. So hours instead of days. That is one of the keys here. So now we have a demo time here. So yeah, I will switch over to Anders here. Do you see the green desktop here with the?
Do you see the ThinLinc desktop?
I see demo, a yellow
okay. What?
Okay, then we have to do something.
Now it's a green desktop.
Yes.
Okay, good. So now you see the standard view that a user sees when he or she logs on to LUNARC, or our HPC desktop. So this is the good and old standard ThinLinc desktop, very well working, very well performing. I just go through, we added some, using the desktop customizer, we added some custom flavor to the menus. So we have, this is changing all the time because users have new needs and we're changing these menus, but this is the current state where we have some different apps. And worth to mention is that all these applications run on the application server that best suits this application. So it could be a guy with a lot of memory, or a beefy graphics card, or a less beefy graphics card, or something else. So it's the shared application server mechanism. And down here we have the on-demand, on-demand system that launches applications either on Linux bare metal servers or on virtual machine. And we have some support tools, and we have some specific LUNARC tools, and so on. So without further ado, I will start one application running on the shared system, and I choose VolView, which is a volumetric rendering application. I will explain what happens. Can we? Yeah. Okay. Here we go. VolView. So now I'm loading a data set, and now it's actually full screen. Maybe I can try to
Import.
No. Just would like to do this window slightly smaller so you can see what's happening here. I think it's loading. So this is just a volumetric rendering application, and I'm using an open source data set. So this is running off a separate server. In this case, it's called GFX0, having a K80 NVIDIA card, and the pixels are injected into the 2D desktop. And this window is transferred using the visual transport mechanism. And I can do some simple lookup table changes to visualize this in different ways. But it's very well performing. I hope you see have the same experience across Zoom, but here the frame rate is very consistent and it's very fluid. Okay, so now Jonas will continue with some other demos. Now I just changed the LUT to another LUT. It's the same data set, but I'm just changing the lookup table to show different aspects of the voxels.
So now I will show you the graphics launcher user interface. I will go into the on-demand desktop here, and I will open the church I showed you before here using PhotoScan, which is the tool that archaeologists are using. So now you see here the PhotoScan user interface here. The first box here, you can select wall time, so 30, 60, 6 hours, 12 hours, 24 hours. You can specify specific resource information, features here, so I can select different, how many GPUs I want to use. So let's take a 2 GPU. You can start the application by pressing start. You can also see some more information here if you're technically interested, and there is also a way of seeing the actual Slurm script that is being submitted. So you can hide that as well. So I press start here.
So the difference between the former thing I did and this is that now Slurm allocates a bare metal server in this case that the user owns for the wall time period of time. What I did before is I launched the application on the shared system. So that's the difference.
Now we are loading. This is a quite large model. So if you look here on the left here, we see we have 3.5 million faces that are rendered in this model. So now I can rotate this around on the screen. And we can zoom in here to see this very nice textured image. And we can zoom around here. And we zoom in here a bit just to illustrate how many faces there are. So you can see here that this is there's quite a lot of faces here in this model, and we can work with this in real time. Just going to switch on here again, like that. So this is this is what they're using to kind of work with their reconstruction. So this program contains a workflow for importing the images, aligning the images, but it's entirely, they do it mostly interactively. So then you can close the program. And the next demo I will show you is ParaView. So we have also here running ParaView 5.8. And I will load a model here. I can do it like this instead. So this is a vector field here. And just to show you here, I can just add some streamlines. Streamlines, and then I want to show you how the model as well here. So I turn down the opacity here. So as I can work in real time with this here. I can do some filters on it. So working with ParaView works very easily. You can do interactive work. But now you're running on a hardware accelerated server in the Elvis cluster. And now you also see when I stop the application here, the ParaView interactive here will automatically detect that the job has completed, and you can start the application here again. We can also do Jupyter Labs. So that is something that has been popular here, is running Python in an interactive way. And that is web-based, so it starts a web-based tool on the node. But we use the same method of starting here. So I just put start here. It takes some time to start up here. It waits for the job to, the output of the job to produce the URL for connecting to this, this web server. So now it automatically starts Firefox. And you can see here, now we are connected to the node AU007 here. So it's a secret agent node. And here you can run your Jupyter things here. But what you also can do is actually you can have interactive access to the node. So by using a feature built into the Jupyter Lab here, we can launch a terminal, and we are inside a node here. And I have my files available here, and I can do interactive work as well from this web-based interface. And also, if I should mistakenly disconnect my session here, I can click the button here to reconnect to the lab.
The other clarification, AU is a node in the Aurora compute cluster, opposed to nodes of the graphic cluster.
Yeah. So this is normal HPC node.
Mm.
So the final thing we want to show here is the Windows application here. So starting Windows application, we do the same thing as for the other type applications here. So I just press start here, and what happens now is it submits a job to the special virtual node, and that will launch a virtual machine on the hypervisor. So it takes some time because it makes a full startup of the Windows operating system here. So we should be seeing this shortly.
We have chosen to have different frame buffer configs regarding the vGPU slices. And we have ended up using like t-shirts, small, medium, and large, depending on the kind of job you would like to do and the application you would like to launch. So when the connect to desktop button is available, it's possible to connect to the Windows system. And as you can see, it's connected to our domain ad.lunarc. And the same username in this example is BMGL, is populated in the user dialog, and Jonas uses first factor to authenticate. And as a matter of fact, we discussed it back and forth and decided that since many users are coming from Windows side, they appreciate having a full-blown Windows desktop, because they're used to features like File Explorer and other Windows tools, opposed to the Linux equivalents. So actually, if you maximize this window, it looks like a Windows 10 RDP session. So you can more or less obscure the Linux parts. And as Jonas shows us, we have the protocol server serves the same data to Windows as is visible from Linux, meaning that we can go back and forth between the different OSs accessing the same files.
Yeah, exactly. The same files here as we have in the other window. And just to finalize the final demo here, we'll show you a data set in the Imaris application viewer.
It's a microscopy viewer. Well, a view of where you can view microscopy data. And I think you loaded a volumetric data set. Yes. And
we can rotate it here on the screen. And it uses the backend GPUs for the graphics rendering. Yeah.
Yeah. I think we're running over time here, but I think you can cope with us.
Okay, so that was the final demo, I think. So we'll go back to our slides and try to finish off here. So, and finally, so GFX Launcher in the 0.6 version is available open source. So if you want to try it out and configure it for your own system, it's available here on GitHub. So you can send that information out later, but you just search for GFX Launcher on GitHub, you will find it. There's also documentation available of how to configure it and use it in your own environments. Currently, it's adapted for, of course, for the LUNARC environment, but I think with the configuration files, you can manage to configure it for your own environments as well. So that was our final slide. So here's some information here, and you can get information on our LUNARC website here as well. We also have a Twitter page if you want some more information on our ongoing work. So thank you very much.
Thank you very much.
Finalizing. Thanks all of you for joining this webinar. Thanks again, Anders and Jonas, for the brilliant presentation. Very informative, and I see that people engaged in the discussion, so I think this confirms how interesting it was. And we hope you had a good session, and we also want to invite the others. Would you like to present your ideas? You are welcome to join the community and share your thoughts and feedback with us. So then you have Aaron's email and mine as well. Welcome to share your ideas. So do you have a final message, Jonas and Anders?
I think we can just say we're happy that we had the opportunity to show you all what we've been doing, and I really appreciate your initiative, John and Cendio, and thanks to Cendio for bringing us ThinLinc, because without ThinLinc we haven't been able to do this in this good way.
Yeah.
Great to hear. So thanks all, and you are welcome to our next session. We still don't have it scheduled. In the near next weeks, I think we'll have that and share with you. Thank you very much.
Thank you very much.
Thank you.
Thank you. Bye.
Take care.
Bye-bye. Take care.